All right. Yeah, welcome back to this course. So we are going to continue from where we stopped. Today we want to look at statistical analysis, focusing on descriptive and inferential statistics. We understand statistical analysis, particularly in R, refers to the process of using R programming language and its extensive collection of statistical libraries, or we call it packages, to analyze data, perform statistical tests, and make inferences from data. We must understand that how is a very powerful tool for statistical analysis due to its rich ecosystem of packages designed specifically for statistical modeling, data visualization, and hypothesis testing. Uh, this analysis actually typically involves the following steps. One, data importing and cleaning. This is very important. That's the first step that every data scientist must perform. We must import the data and clean the data first, or you call it data wrangling. Then we have what they call exploratory data analysis, EDA, which involves examining and visualizing the data set to understand the structure. Right. We also have what they call descriptive statistics, that will describe or summarize and describe the main characteristics of the data set. We also have statistical modeling, which involves modeling, which to fit data fitting and to explore relationship between variables and make predictions or test hypotheses, which we are going to be looking at. Now, we also involve hypothesis testing, testing which is used to make inferences about population parameters based on sample data. We know that we perform a t-test, ANOVA, chi-square, and some non-parametric testing if possible. And we also have model evaluation. So after fitting statistical models, it is essential to evaluate their performance and validity. We also have interpretation and reporting. Data must be interpreted and reported. The result of analysis are interpreted in the context of the research question or problem being addressed. So these are the things that these are just the overview of statistical analysis in general. But we are going to start by a simple definition of what a statistical analysis is. It's the process of collecting and analyzing data, large volumes of data, in order to identify trends and develop valuable insight. It is an important part of quantitative research. You can use it to test hypotheses and make estimates or inferences about populations. So this is the first thing what we need to understand about analysis. So we are going to go gradually look at what is called population sample. In the statistical analysis, we have population is an entire group that you want to draw conclusion about. For example, GDP of all countries in the world. Let's say you want to know the income of all countries. This is not possible actually. You cannot know the income of all the countries. You cannot test on that actually or research on that, but you can take a sample. All right. So we can now say under sample now, which is the specific group from the population used for inference, you can say GDP of countries in Africa, which may be meaningful. You can take population from that. Or let's say we want to have population of a college or college student in Malaysia, for example. We just use a country as a Malaysia, for example. And they might not be possible because you cannot get all the college students in Malaysia. But you can take a sample, as you can say 300 college students from a particular university who volunteer for the study. That might be a sample. Also, we can have maybe advertisement for IT jobs in KL, Kuala Lumpur, and then maybe because of that's just a population actually, but that may not be possible. We can say that a top search result for advertisement for IT jobs in KL as at May 2020. So that is just population and sample. Population is broad, okay? It's broad in its own context, and it's not possible to address the entire population. So you have to take a sample population. That's a research concept. So to use for then you can now infer back to the population based on the the result you got from the sample. All right, so let's assume you have a population of all the women in United States of America. You want to research on them. Maybe there's a pregnant woman in New York. Want to research on them. Maybe say you want to research on their weight during pregnancy. How the weight, how the pregnancy contribute to the weight of the pregnant woman in New York. You cannot get all the women in New York. You can only get a sample. So let's say we get a sample. So this will be a sample. Okay, this particular small circle will be a sample. So we bring this out. We call it sample. All right. So this is target population. All the women, pregnant women in New York. So but we cannot get all of them. So we just take a sample percentage of them, maybe 30%, and then bring it out. So that is what we do, called sampling. So we have what they call sample size. Sample size is a very complicated concept which I don't want to dig into in details because it has so many principles, so many constraints, so many conditions, so many methods. Especially in social science, it's a very broad subject, so you cannot go into it in details. But I want to pinpoint some things here which can be of help for a beginner researchers. Maybe you're a researcher, you're a beginner. You can pick something from this simple example. I want to just pinpoint here because there are 4 things that you look at when you are dealing with sample size. You look at the population size itself. Apart from the fact that you know your target population size is very important. The size of subjects or people that are the main target of the experiment. You must know, which I've given an example just now in the few previous slides. And one of the things also is margin of error. How much error are we willing to allow in the sample? So this can be, maybe we want to allow 5%, which is plus or minus 5%, which we have 0.05. Okay, that's our probability. Okay, that probability we have so that become our p-value. All right, so degree of variability, how much variance do you expect in your response? Assuming if value where p equal to 0. This p is not the p of margin error actually. Okay, it's different. So we have p 0.5. This is for unadministered survey. Our survey has not yet been administered yet. That is when the survey is not yet administered, you assume value p variance of 50%. All right, so this is a 0.5. All right, that is when the software has not yet been administered. This is for unknown population. That's what I meant. Unknown population. You don't know the population yet. So okay, so you just want to this is based on different method which I will explain further. You talk about the confidence level. It is a measure of the likelihood that a hypothesis or prediction is accurate, right? You have 90%, you have 95%, 99%. You understand all these things. So when you take 90%, 95%, automatically you understand that your p value will be 0.05. If you take 90% or 99%, you know that your p value is 0.01, and so on. So this is a confidence level, and these 4 components they are very important when you come to dealing with sample size using the formula I want to present to you. All right, let's assume that we have a unknown population, sample size for calculation for unknown population. Suppose we wish to evaluate a statewide extension program in which farmers were encouraged to adopt a new practice. Okay, this is our research focus now. Okay, suppose we wish to evaluate a statewide extension program in which farmers were encouraged to adopt a new practice. Assume there is a large population, but we do not know the variability of the proportion that we adopt the practice. Therefore, we assume p equals to 0.5. That is the maximum variability. That's the 50%. We assume 50% we part of the program. All right. So we don't know yet. Furthermore, suppose we desire our confidence level is 0.95%. That's our confidence level, which is standard. So you can choose 90%. You can choose 99%, depend on what you want, depend on what I think 95% is fair enough. Okay, It's fair enough. And then we choose our precision, which is a 0.05, which is plus or minus 50, which is 0.05. Okay, plus 0.5% is 0.05. So that is our precision level. Don't forget that is what I mentioned here for our margin of error. That is precision level, margin of error. So now we can introduce a formula called Cochrane's formula. This was established in 1963 by Cochrane, and it deals with a sample size for unknown population that is not known. You don't know population yet, right? So you want to calculate sample size. So you can sample size is equal to z square pq all over e square, where e is the margin of error, which we just explained now. You are willing to allow, which is 0.05. And then we have p, the degree of variability that you are talking about, which is estimation proportion, which is 0.5. That's p. Then we have our q, which is 1 minus p. All right. Subtract 1 from p, give you q. That is the formula. Then z is 1.96. This is a critical value of 95% confidence level per the normal tables. If we check the normal tables, for example, if you look at these normal tables, for example, you see that this is a standard value. We have z is 1.96 at 95% confidence level. If you check the tables, normal table, you see this is standard. For 90% confidence level, you have a z as 1.645. For 98% confidence level, you have 2.33. And for 99%, you have 2.575. So you just choose, because we are using 95%, so our z is 1.96. All right. So let's return back to the formula. So when you supply this into the parameter, to this formula, you have the your 1.96 is given here as your z square. Okay, which is say you square it, then that should 1.96 our z we got from the what they call it now, normal table. Then we have our 0.5 here, which is a p. Okay, and we have our q, 1 minus 0.5 is 0.5 also, then divided by 0.05, and that is our e. Right, our e is that's the margin of error. We square it, so total will give us 385. This is 385 we have now. This 385 is the amount of the population. I mean sample size. All right, that's our sample size. Our current sample size is now 385. So that is very simple enough, right? So very simple to understand. Formula is very straightforward. So it's a random sample of 385 farmers in our target population should be enough to give us the confidence level we need. This, but I will suggest that you don't just take a sample of 385. Okay, by experience, you take a sample of 400. Okay, so that just suggested because of outliers and the rest of them. So that anything because of those kind of possibilities, just take a 390 or 400. Then so that should be okay. All right, but at least your population, your sample size is around this range, 385. Okay, so you can take 400, or to be on safer side, 400 or 390. Then you can filter later and let 385 remain. You have the best sample size. So, but what of when you have a known population that we already know that okay, this is the population of the people. What sample size do we need from it? Suppose our evaluation of farmers' adoption now of the new practice only affected 2,000 farmers. We know that we already have 2,000 farmers that we subscribe for this particular new adoptions, new practice. Okay, the sample size that will now be necessary is calculated thus. So we use what is called Yamin formula. This is established in 1967 by Yamin, and the sample size is n all over 1 plus n e is over 2, which is equal to 2,000. We supply our n, so we already have n, which is known population size, 2,000, or divided by 1 plus 2,000 into 0.05. Don't forget our e is equal to margin error 0.05. Then our n sample size, which is this, so we already know that. Then we get 333. This is new sample size now. So if you want to do a proper experiment, you don't use 333, you can use 340 or 350, okay, to give room for outliers. So 340 or 350 is okay, then you can now filter later. So this is how you carry out such thing, population out, I mean such experiment to make life easier. So, and I think this particular simple formula should be good enough for us for any experiment. It's very, sample size is very broad subject in research, okay? But I just want to help someone to make it easy for you to, don't forget to cite your mean if you are using for non-population, or the other one, Cochrane's formula. You have to cite when you are, to let them know that this is what you use to calculate your sample size, and it's good to go. Don't need to struggle. All right. So that is that for that. So you can Google online to check for the citation or the material online, and you can cite it, and to know that this is what you use. And that should be enough. So let's go further as what we are talking about today: descriptive and inferential statistics. Descriptive covers statistical method for describing data using statistical characteristics, charts, graphics, or tables, where you look at some parameter like a mean, mode, median. Inferential is a branch that uses various analytical tools to draw conclusions about the population from the sample data, which is very important. So inferential, it gives back to the population. That's what it means. If we look at this now, this population of people, okay, and we are taking sampling. Sampling is not yet sample, is the number of sample in process. We call it sampling. All right. So now we have sample here, which we finally got after we have filtered, we have taken a necessary number of sample we want. So the descriptive stop at this point, does not go further beyond this. All right, because essentially descriptive statistics state facts and proving outcomes from a population, whereas inferential statistics analyze sampling to make prediction about larger population. So it's now inferencing, so it's giving back now, try to infer back to the population. That is inferential now. All right, so we have a general tendency in descriptive. We are talking about mean. The mean value of your data is the average of these numbers. We have mode. The mode represents the most frequently occurring value in the data set, and we have median. When you sort your data by size, the median is the value in the middle. So these are very important elements in descriptive statistics. We also have a spread of this or dispersion in the descriptive. We have minimum and maximum, which is for range. We have a variance, the average square deviation from the mean. We have standard deviation, SD, the average deviation around the mean. We have interquartile range of the middle 50% of the data, the difference between first and third quarters. So these are very important concepts in the descriptive analysis. All right. So we need to understand that descriptive statistics describe the characteristic of data set under study without generalizing beyond the analyzed data, okay, which include the measure of central tendency that I just we just mentioned now, mean, mode, and the rest, measure dispersion such as a range, variance, and we also have frequency distribution, which like from time histogram, frequency tables, and graphical representation, to like box plot, bar plot, pie chart. All this one, they are involved in descriptive statistics. But inferential allows researchers to draw conclusions, test hypotheses, and make predictions about populations, even when it is impractical or impossible to study the entire population directly. Okay. All right, that is inferential for us. So testing whether the pattern that you observe in a sample are likely to be present in the broader population or just a product of chance. So testing statements about the population on the basis of the sample characteristic, that is inferential. So that is a sample, and then we are that to make an inference on the population. Okay, that is inferential. All right. Under inferential, we have what they call parametric and non-parametric tests. Right. Parametric tests have some what they call assumptions. All right. assumptions. Now we are going to look at both parametric and non-parametric later, and how do we handle this as under this particular course. But at least we need to understand the assumption of parametric tests first, which one of them is called normality. All right, the sample data come from a population that approximately follows a normal distribution. Okay, normal distribution. If you check last time we looked about normal distribution, if you understand properly, we brought the curve using density and the histogram to show normality of a curve of a data. And we also have another one called homogeneity of variance, right? The sample data come from a population with the same variance, right? The same variance. So we have, if it is maybe the variance on the left must equal to the variance on the right. You must have the same variance throughout the groups of the population. So we also have independence. The sample data consists of independent observations and are sampled randomly. This is not manipulated data. Some data are manipulated. This is the original data that are taken, okay, independently. All right. So we also have outliers. The sample data don't contain any extreme outliers. Not that I cannot find outlier in between, but it must not be extreme. It must be minimum. All right. So these are assumptions that must be observed during parametric tests. So the data must be normal. It must be homogeneously variance. It must be independent. It must be independent, and it must avoid of outliers. All right. So these four, they are very important parameters or assumptions you need to check if you want to perform parametric tests. All right. We have parametric tests such as t-test, ANOVA, chi-square, correlation, regression. Chi-square is could be called parametric. Sometimes it's also used in non-parametric because it only deal with categorical data, not a numeric data. All right, so you don't really require, it does not really require assumptions. Okay, so it's a outside the assumptions we mentioned. Chi-square is outside it because it can be parametric and non-parametric. All right, so because it deals directly with a group data, which is called categorical data. Example, age, which is male and female. I mean, gender which is male and female. So these are categorical data. They are not actually numeric data that you have to look at, check for normality, check for test variance, variance test. No. You don't perform such on chi-square. So that could be parametric, sometimes not parametric. Anyone could be used if you want to test for proportion, for example, or independence using chi-square. All right. We have a correlation assessing the relationship between two numerical variables. We have regression, allows you to predict the value of a variable, which is dependent variable now, based on the value of another variable, which we call independent variable, that is x. All right. So we have x, we have y axis. So you look at the progression of the slope, how it goes. If there's we can predict anything positive or negative. All right, so that is that about that. So we must understand that the parametric test is robust. Yes, that is the good news. Parametric test is robust. It means that even if a normality assumption is violated, don't forget, if a normality assumption is violated, not all, okay, we can still use parametric procedures. Maybe one of the assumption fails, for example, one of them fails, then you can still proceed with the test and it should be accurate. You can still use parametric procedures. So, but all must not fail. Okay? If any one of them fails, maybe normality, maybe homogeneous, native failed, or maybe independent, or maybe outlier, whatever any one of them fails, you can still proceed to with a parametric, because parametric is actually is robust actually. But large sample size will help a lot. We help if you have a large sample size under this condition, or if and at the same time your group sizes, equal group sizes also is very important. Maybe you have a group data there which is called gender, for example. You have 10 male. You cannot have 20 female. You must have 10 male, 10 female. That's what it means. All right. Or you have a age group, for example, age group. maybe you have a maybe children, you have adults, you have elders. So for just a fertility group, those three groups must be equal, okay, equal size of groups. So that will help your parametric test a lot to make it more robust, because when they are the group sizes are not the same, it affects the results, okay, on parametric test. So you have to take of that. So however, you be aware of multiple violations. Therefore, when the assumptions are too badly violated, then use non-parametric. All right. So that's when non-parametric comes in. Maybe the first one fails, second one fails, third one fails. Oh, they are all failing. Then know that this is not a data for parametric procedures. So you use a non-parametric test to calculate your data. So that should help a lot. But don't forget also that we have some kind of chart we draw for each of these parametric tests and non-parametric tests. But that's not for now. I think I will pinpoint on that later. But when you are dealing with parametric and non-parametric tests, we have these particular tests each of them have a counterpart. For each parametric test, we have non-parametric tests for it. Okay, like I said before, chi-square could be used for parametric and non-parametric at the same time, because it's only based on categories, categorical data only, not on the numeric data. Okay, so if you want to check something on categorical data, maybe you want to set for a proportion of the categorical data, you can use chi-square, what they call test one some proportion. We call it goodness of fit. Okay, or you want to test for independence, maybe two categorical variables, for example. Chi-square is also there. We call it test of independence or independence test, right? For either for parametric or non-parametric. So we also have one sample t-test. So you can say a simple t-test is good enough for parametric, and the reconstruction test for non-sample is for non-parametric. So we have two independent sample is unpaired sample t-test. We have Mann-Whitney U test. U means unpaired. Okay. We also have two dependent samples. We have paired sample t-test. We have signed ranked test. And we also have when it's more than two independent samples, okay, then we say one way ANOVA. All right. Then we have Kruskal-Wallis test for that under non-parametrics. So we also have when we have two independent samples, one way repeated ANOVA. We have Friedman's ANOVA. All right. So this is another non-parametric test to replace that. When you are dealing with between two numerical variables, for example, Pearson R correlation is there, and for non-parametric we have a Spearman correlation. So these are the two categories of a test we perform under inferential majorly. So if parametric does not assumption could not be assumed is violated or violated, just switch off to number. I don't want to. There's no time to be giving why parametric, or what are the differences. That's not the time for that for now. Okay, but at least parametric is not too bad, even though it does not follow much assumption and does not give back to population. But yes, it's still a very powerful test. All right, so we have what we call hypothesis testing. Hypothesis testing for testing a claim about a parameter in a population using data measured in a sample. For example, you may want to test a question. For hypothesis, a question must be developed first. Of course, must have a question first, such as does eating late at night really cause stomach protrusion? That's just a sample question, for example. You now have maybe this is a question on this underlying question now. Okay, for you to investigate this question now, you have to develop hypothesis, which is you have to have null and alternative hypothesis. So we have this alternative, not alternative. All right. So pardon me for that. So we have eating late at night does not cause stomach protrusion. That is null hypothesis. If not, or alternative says eating late at night does not cause does cause the malpopulation. So we have two hypotheses now. This one is clear that eating late at night does not cause it. Our major focus is eating late at night does cause tumor malpopulation. That's our major focus. But we have to first nullify it by using null hypothesis. Okay, so if we do our testing, carry out our testing by setting our parameters, our threshold of a probability threshold to 0.05, and then we run our test. If our value, depending on what we get, we can reject one and we may not reject the other. All right. So that is hypothesis. This must be done before the test begins. You must understand your question and then set hypothesis for it. Then because you are testing actually for this particular second one, eating late at night does cause tumor malpopulation. So, but you have to first negate it first. Okay, this is called null hypothesis. You have to negate it first. So by saying that late at night, does cause tumor malpopulation. All right. So we have a confidence and signal level. The confidence level is the probability, which is 1 minus alpha, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. So each time we repeat, we have only the same confidence level, okay, which it could be 90%, 95%, 99%. So the value of alpha is called significant level, which is known as p-value. It's generally known as p-value, probability value of an estimate. So we have basically 3, though it could be 4, like some 98 could be included, but generally we have 3, okay, as a standard 90% confidence level, 95% and 99%. So for each of these, they have its own significant level. So which means when you subtract 1 minus or 100 minus this, you have 10 left, right? We have 100 minus this, we have 5 left. 100 minus this, we have 1 left. It should give you give one 0.1, give one 0.05, and 0.01. So when you choose confidence interval of 95%, automatically you have a 0.05 signal level. Your p-value will be 0.05. So that's where you need to check your probability if your test is significant or not. All right. So so that is exactly what that means. But if the p-value is less than the predetermined threshold, the result is considered statistically significant, which means we have enough evidence to reject the null hypothesis in favor of alternative hypothesis. So that is exactly what I'm talking about. Then we have a confidence and significant level as well. For example, now this is what I just described now. At 90-degree confidence level, if p-value is less than 10%, which is 0.1, then we reject H0, which is another hypothesis. At 95% confidence level, if p-value is less than 5%, we reject H0, and likewise at 99%. So that is that for now. So we're going to go into the practical section, and we'll see how to actually do statistical analysis using parametric tests and later non-parametric tests. Thank you so much for listening. I will see you in the next class. Thank you.